let me briefly go over what we were doing last time. So last time we started to take a look at this finite element implementation of the one-dimensional basis functions that we introduced. So we said that we are going to try to solve the same problem, but instead of instead of assuming global shape functions, we are going to concentrate our attention to one element. So this is the quote-unquote element point of view, if you want to think of it that way. And we introduced the same approximation that we did for the one-dimensional basis, the exact same hat shape functions, but when we restrict our attention to one of the elements, what we said was that we could write the virtual work functional as a sum of integrals. So there's nothing new here. And we were able to express our displacement approximation within an element in this manner. So this is normally called the shape function matrix n, and this is a standard notation for all types of finite element formulations. You have this shape function matrix n multiplied by the solution degrees of freedom, and if you express it that way, you can see that in the case of our linear shape functions, we just have the first function that has the value 1 at node 1, and it goes to 0. So this is true again for all types of finite elements, where if you have a nodal shape function, it will go to the value 1, and it will be 0 everywhere else, every other node. So once you introduce this approximation for your solution, you can take the derivative of this. So this is what this says is that you can find the solution, you can approximate the solution at any point in the element in this manner. So note that this is a scalar function of a scalar variable x, and it is expressed as a matrix times a vector. So this matrix itself has its entries, which are functions of x. This one is a matrix of constant coefficients. So if you take the derivative of this, that will give you a measure of strain. Okay, so the measure of strain, approximately you can find the strain at any point in the element by just taking the derivative of this n shape function matrix. What you will get is this b, and this b is nothing but the strain displacement matrix. So finally, all that you have to do is to substitute these two approximations back into your weak form, and if you do that, we saw that for each element. Now this was the original weak form that we had said for the continuous problem, when we do not make any approximations. This will be approximated by introducing our finite element shape functions, and we are going to denote that approximation with this g tilde of h, and h again just denotes that it has been discretized. So in this case, this g tilde is a function of your nodal degrees of freedom. Okay, and if you substitute that in, all you get is the sum of all these terms over each element. So this, we said last time, was the stiffness matrix. Now, is this somewhat familiar to you? Maybe in structural analysis, when you did it came out to be B transpose DB or something like that. So this is the exact same formula for linear one-dimensional finite elements. And once you have this element stiffness matrix, this is also the same thing that you have to code up, by the way, in your homework 3. This box formula and this box formula, how you want to do the integral is up to you. So this is the element stiffness matrix. This will be a 2 cross 2, and this is the load vector. This will be a 2 cross 1. Okay. And if you write that out all in an expanded form, what you can do, you can see that this is a 2 cross 2 stiffness element stiffness matrix multiplied by the nodal degrees of freedom within the element. And then the thing to note that we said last time was that the degrees of freedom at a node, let's say this is node element E, and the node this node is shared between two elements. So the degree of freedom 2 from this element is equal to the degree of freedom 1 from this element. So when you take that into account, you can take you can say that this is equal to this, and this is equal to the degree of freedom 1 from the node from the element 3, and so on. And if you do that, what that means is that you are going to assemble the equations. And again, this is a fairly simple concept, and hopefully most of you should have seen this before. But all that you have to do is to assemble all your degrees of freedom in the according to what they are uh, in the global coordinates. So this becomes all your virtual displacement degrees of freedom, and you can assemble this big stiffness matrix. This is the global stiffness matrix, and all that you are doing here is assembling the small. This is a small element matrices. So this is the element matrix for element 1, element 2, element 3, and so on. Let's say there are m elements, okay? And the thing to note here is that the common degrees of freedom just simply get added. And these are your unknown solution degrees of freedom. So once you do that, um, you can also express your right-hand side load vector. And last time we said that any nodal loads that you have can simply be added to the corresponding degree of freedom wherever it needs to go. So in this case, our nodal load is acting at the end of the bar. Okay. And finally, you can write this. This becomes your discretized weak form. So all that you need to do to you should recall that what we had said earlier, that we want to make sure that this discretized weak form is 0 for all values of virtual degrees of freedom. And that can be made sure by just solving for this term to be 0. Once you solve this term to be 0, then doesn't matter what d bar you choose, this g will be 0. So that's the basis of saying that for all values of d bar, this g has to be 0. Okay. And then we also saw how to actually enforce the boundary conditions, because in this case we chose functions to be nice within an element, and they need not satisfy boundary conditions. So did anybody try to figure out in MATLAB how you can do enforce these boundary conditions? It's a one-line statement. And just to give you a hint, it's called array indexing. So if you have one array, you can pick out the specific entries of that array by. So normally when we want to access array elements, we say array A parentheses that index. Is that right? So instead of saying parenthesis one single index, you can actually provide array A another array as an index. So it will pick out all those entries from that matrix. And you can take a look at the getting started portion of the MATLAB that I had originally posted in homework 1. They actually have this thing about array indexing. All right. So ultimately what you want to solve is this equation. So once you enforce your boundary conditions, all you are trying to solve for is this. Once you know this, you can go back and calculate your reactions. And then in the post-processing, once you know the solution, you can again go back within each element and try to find what the solution, what the stresses are within that element. All right, so let's take a look at some of these properties of the stiffness matrix. So this is the global stiffness matrix that we said that we are going to assemble from all the element stiffness matrices. So this bold A face operator, I'm denoting it to be an assembly operator. Yeah, Rachel? Any extra copies of the notes? Just one? Okay, there are some. All right. So yeah, we'll assemble the element stiffness matrices to form our global stiffness matrix. And this element stiffness matrix, all that you have to do is to solve, this is the expression for the element stiffness matrix. And just writing out again in the form of the boundary conditions, normally what we say that the equation that we are trying to solve is k times d is equal to f, where this f, the right hand side vector, I'm denoting it as an effective force vector. So this effective force vector is nothing but what we had before, the actual force vector minus the forces that are coming from the specified portion of the boundary. Okay, so once you solve for this, you will have the solution. But the critical question is, can we actually always solve for this df? So this is a system of equations, system of linear equations. And let's say there are n free degrees of freedom. So this matrix is an n cross n matrix. This unknown solution is n cross 1. This force is also n cross 1. So essentially what we're trying to solve is n equations and n unknowns. Can we always solve that? Obviously, it depends upon what matrix you have. If the matrix is singular, what does that mean? Determinant of that matrix would be 0. But does that mean that the solution doesn't exist, or does it mean that, what does it mean? Sorry? Say that again? Yes, if the stiffness matrix has is singular, then we cannot find its inverse, which also means that the determinant of that matrix would be 0, which also means that at least one of the eigenvalues would be 0. Okay, so yeah, one way of trying to find out whether this system of equations can be solved is by using the concepts of eigenvalues and eigenvectors. So going back again to the same point, let's say this is singular, and let's say this is one of the eigenvalues is 0. So does that mean that there is no solution, or are there any other possibilities also? So maybe just to take a look at, as an aside, if I say that I have a system of two equations and two variables, so let's say this is x, y, a1x or a11 and a12y, a21x plus a22y is equal to b1 is equal to b2. So if you write it out in the matrix form, this would be this 2 cross 2 matrix, vector of unknowns is equal to right hand side. And we know that these two equations would be straight lines, something like this. And the solution that we are seeking is their intersection. So let's say this is the solution x0, y0. So when I say that this matrix is singular, then the determinant of that matrix would be 0, which says a11 times a22 minus a12 times a21 is 0. What does that mean in a geometrical sense? They are parallel or overlapping, right? So the only two possibilities would be that those lines are either parallel or they are actually overlapping. So in one case, if they are parallel, then there is no solution, right? And if they are overlapping, then there are infinitely many solutions. Does that make sense? Okay. And how do we find out whether they are parallel or overlapping? Sorry? Yes, so it depends upon the right hand side. So Another way of saying that is that we have this matrix. We have this matrix A, this unknown vector that we are trying to solve, and this right-hand side B. So there is something called the range of A, the range space of A. What that range means is that if you take some vector x and you multiply that with A, let me write that out. So you have this matrix, you take some vector v and you multiply it with this matrix A. So the space of all these vectors, that's the range space. So if you take any vector, multiply it with the matrix, you'll get another vector. And if you take the collection of all such possible vectors, then that set is called the range of that range space of that matrix. And clearly, in this case, if the matrix is singular, you take any vector and you multiply that with the matrix, your vector will be pointing in this direction. Okay. Now what that means is that if your B vector, if your right hand side vector is also pointing in the same direction, then you can solve for, there will be infinitely many solutions. So if right hand side is within the range of this, this matrix, then you can solve and there will be infinitely many solutions. But if the right hand side vector B is pointing in some perpendicular direction, or actually has even a slight component in a direction that is not along this line, then there won't be any solution. Okay, so this is just a little bit of properties of matrices that you should remember, especially for this course, because again and again in this course we'll be solving equations like this, and whenever we are trying to solve equations, we need to be able to know whether even a solution exists or not. Okay, so this is the same equation that we had just now, and we are trying to solve this equation. So to find out the eigenvalues and eigenvectors of A, that will give us an idea of whether this system is singular, whether this can be solved or not. So how many of you remember how to solve for eigenvalues and eigenvectors? Okay, I guess those of you who don't remember need to go back and take a look at, or make sure you remember how to do this. So the essential definition of eigenvalues and eigenvectors is right here. If I take this matrix A, this is the matrix equation that I'm trying to solve. Or in our case, we are trying to solve for some k times d is equal to f. So if we take this matrix equation, if we take this matrix and multiply it with some vector v, we should be able to express this as a scalar times the same vector v. And if we can do that, then this vector v is an eigenvector, and this lambda, the scalar, is an eigenvalue. Okay. And another way to write the same thing is that saying that determinant of the matrix A minus the scalar times I is equal to 0. So is this equation familiar to you? Okay. So this is the familiar equation for eigenvalues, how we find eigenvalues. And we'll take an example of that in a little bit. But let's take a look at what are some of the properties of our K that we have obtained. We said that our element stiffness matrix was going to be symmetric, right? That is straight away from the first line right here. So this is the same vector multiplied by another vector transpose. And actually what you can do is take this constant c, the scalar, to the left-hand side, and what you're left with is this. So this is a 2 cross 1 multiplied by a 2 cross, or a 1 cross 2. This will give you a 2 cross 2, which is symmetric. So once your element stiffness matrix is symmetric, and all your degrees of freedom in the global system are also um, ordered in the same way, then your global stiffness matrix that we constructed by assembling all these element stiffness matrices, there, this is also going to be symmetric. And when we restrict, when we divide this global stiffness matrix into two parts, the specified and the free parts, even then those this matrix is going to be symmetric, this matrix is going to be symmetric. How about this? Is this symmetric? Is this matrix going to be symmetric? It's not symmetric. It might not even be square. It might actually be rectangular, right? But if you take the transpose of this matrix, that will be equal to this. Okay. Um, so one property of this K matrix is that it is symmetric, and what that means is that eigenvalues are going to be real. And why is that important? Because when we want to solve for our unknown vectors, we shouldn't be getting complex displacements, right? So symmetric matrices have eigenvalues that are real. And it also means that there are some specific types of solvers that we can use for symmetric matrices that are more efficient than general solvers. And another thing that we noted last time was that this was banded. This stiffness matrix was banded, meaning that there is a main diagonal, and if you actually rearrange your equations in such a way so that it can form this band, then you can minimize the amount of time that is required for solving these equations. And the number of entries that are non-zero starting from the diagonal away, uh, the number of non-zero entries in any of the degrees of freedom or in any of the rows is called the bandwidth. And this is some terminology that people who write solvers use. So these types of matrices are also called sparse matrices. Sparse because most of the matrix is actually zero. Only there are very few non-zero entries, and this is also true for 2 dimensions, 3 dimensions, and so on. The only difference here is that in 1 dimension, the matrix that we got was a tridiagonal matrix. But in 2 and 3 dimensions, you actually have to renumber the nodes in such a way that your bandwidth is minimized. Okay, we'll take a look at that when we get to 2 dimensions. But one of the important properties is that this matrix is a positive definite matrix. And what does that mean? Um, I think this might not have actually come out right in your handouts, so you can make those corrections. So a matrix is said to be positive definite if the first condition is that you take any vector C, whether it can be 0, non-zero, positive, negative, whatever. You take a C vector and calculate this product. So C transpose times A times C. If this is 0, if this is greater than or equal to 0, then we can surely say that this matrix is positive definite. Okay. Now, it also means that I could choose I could choose C is equal to 0. In that case, this equality would hold. So what this statement says that for any C, if this is greater than 0, then one of the conditions for positive definiteness is satisfied. The second condition is that if indeed this is 0, if this is 0, then that implies that C is 0. There is no other, this product will not be 0 for any other C. Okay, so these two conditions taken together define a matrix to be positive definite. And when a matrix is positive definite, all the eigenvalues are strictly greater than 0. No eigenvalue can be actually equal to 0 in this case. So a positive definite matrix means all the eigenvalues are strictly greater than 0. And this again has some benefits in terms of the solvers. And here is a small note. So this element stiffness matrix and the global stiffness matrix, this global stiffness matrix was obtained from assembling all of these element stiffness matrices. These are actually semi-positive definite matrices. What does the semi mean? It means that uh, the eigenvalues can be greater than or equal to 0. So if you try to solve this equation, now note that I'm saying that the stiffness matrix, the global stiffness matrix is semi-positive definite, means that one of the eigenvalues is going to be 0. And if you go back to this equation right here, this is the global stiffness matrix, and this is the unknown vectors, unknown displacements. Part of them are known, and this is the right hand side. If you try to solve this equation, you will see that this global stiffness matrix is singular. And what that means physically is that you have this entire big structure. There is no, you're applying some forces to it. It can be in equilibrium at this place, or you can take that structure, move it to a different place, give it a rigid body translation. It would still be in equilibrium. So the solution that this solution would not be unique. It can be translated by a rigid body translation. So that's why this is a positive semi-definite equation. On the other hand, this, after you enforce your boundary conditions, this matrix, this is a strictly positive definite matrix. If your element formulation is good and if you have implemented it correctly, this will be a strictly positive definite matrix, which means that the solution for these unknowns is going to be unique. Okay, so there are some eigenvalues which are going to be 0 in this case, and on the next page we have an example of this. So let's consider this one element. Okay, so this is an element E. Let's say this is the element. I'm applying a force F in this direction and in this direction, so it is in equilibrium. Now I can take the same element, translate it to any different place. If I'm still applying the same forces, it is going to be in equilibrium at any place. So the way that depicts, the way that manifests in terms of matrices is like this. So essentially what we are saying is that we are going to try to solve this equation. And this is the equation that, this is the stiffness matrix for one element. This is the Young's modulus times area of cross section divided by the length of the element, 1, 1, minus 1, minus 1. And this is the, let's say the unknown displacements is equal to right hand side. So on the node 1, I'm applying a force in the negative direction. On node 2, I'm applying a force in the positive direction. So if I try to solve this equation, solve this matrix equation, then in this particular case, I cannot find D1 and D2 uniquely. And the reason is that if you try to calculate the eigenvalues of this, so you take the same matrix, minus lambda times I, minus lambda times I, and you are trying to solve for this lambda and the eigenvectors. So we said that determinant of this A minus lambda I should be 0. That determinant is right here, which is 1 minus lambda times 1 minus lambda minus 1. And if you try to solve this equation, what you will get is lambda square minus 2 lambda is 0, which means that one of the eigenvalues is 0, which is expected because this is an element stiffness matrix which is not being constrained by any boundary. So since one of the eigenvalues is 0, we try to find its corresponding eigenvector, and you will see that the corresponding eigenvector is this, A and A. A can be any constant. So what does that mean again? You have node 1, node 2. You displace the same two nodes by the same amount A. That's your rigid body translation. Okay, so the eigenvectors corresponding to the 0 eigenvalues are actually the rigid body modes. Okay, and the other eigenvalue that we have will be lambda is equal to 2, and you can actually multiply the factor that was up front. And this mode, the eigenvector corresponding to this mode is plus A and minus A. So what does that mean? If I give a plus A to this side, and minus a to this side, I'm trying to compress this element. So this is a pure deformational mode. Um, so the eigenvalues, the eigenvector corresponding to the non-zero or the positive eigenvalues, they are deformational modes. And the same analogy actually holds for the entire structure put together. What we just did was for one element. You can take the entire structure put together. You have the global stiffness matrix. If you do not enforce the boundary conditions, then you will not have a unique solution. Um, and some of the eigenvalues in that global stiffness matrix will be 0. On the other hand, like I just mentioned, once you enforce the boundary conditions, you have removed all the rigid body modes, and that will give you a unique solution. Okay. Um, so any questions on this? Are we going too fast or too slow? No? Okay. All right. So let's talk about some convergence problems, convergence issues that we have. So to actually determine whether your finite element is going to converge, your finite element formulation is going to converge as you increase the number of nodes, that's the business of mostly mathematicians. They try to figure out using functional analysis whether a particular element that you've invented converges or not. But we will just use these results that we can get from those functional analyses. So one thing to note here, I've already mentioned this, is that this was the example that we coded up with 4 finite elements. This black curve was the exact solution, and the blue curve was the finite element solution. So black curve, I'm denoting it with ux. This is the exact solution. And the blue curve with the dots are the discretized finite element solution. Okay, this is an approximation. So we said that it can be shown that the finite element solution at the xe, at an xe where xe is the actual finite element node. So at those nodes, at least in one dimensions, it matches the exact solution on the dot. In 2 dimensions and 3 dimensions, this actually does not hold. So this is a characteristic of one-dimensional finite elements only. Then we are going to also define something called a point-wise error. So obviously the error at the nodes is 0, but how about the error between the elements? So if you pick some point arbitrarily along the domain x, we can define our error as the finite element solution minus the exact solution. So that's our definition of the error. And whenever I write 3 triple lines, what I'm saying is defined as. So error is defined as finite element solution minus exact solution. And so this is the result that we get from functional analysis, and where we try to actually use a Taylor series approximation for the solution at this point in terms of the solution at the node. So if you do that, you can show that the error at any point in the domain will be proportional to something called h square, and where this h is nothing but the length of this element, the element size. So in this case, there are 4 elements, so the length of the element is this size of one element. And you can try to imagine if there is a big structure, you have decomposed that big structure into small elements. So the size of each element, that is the h that we are saying here. So this result, again, what it is saying is that for linear polynomials, and I'm denoting that by this script p to the with a superscript 1. So what I mean here is the space of polynomials of linear, of first, where x can be of power 1. So that's the space of linear polynomials. If you do that, then your error is proportional to h squared. And what that means for us is that if you have a big structure that you have decomposed into small parts, if you half the element size by increasing the or doubling the number of nodes or doubling the number of elements. If you reduce h by half, your error will go down 4 times. Okay, so the same thing here. Here we had 4 elements. If we increase the number of elements to 8, then the difference between these two curves is going to go down by 4 times. So that's a very good characteristic for finite elements. Um, but the error in the derivative, and then remember that derivative of the solution u is going to be strain. You multiply that with a constant, you get stresses. So the derivative, the error in the derivative is only of order h. So what that means is that if you increase the number of elements, so here we had 4 elements, if we increase the number of elements to 8, the difference, this difference between the finite element solution and the exact solution is going to go down by the same amount. You triple the number of nodes, your error goes down by 3. So this is this relationship is that the error in the derivative is 1 order less than the error in your displacements. Is that okay? And in general, this also holds true for any higher order polynomials. So right now, what we just talked about was linear, first order polynomials. Now, a little later on, we'll see how we can have quadratic or cubic or any higher order polynomials. So if you choose polynomials of a higher order, let's say quadratic, which would be p is equal to 2, or cubic, this superscript p is equal to 3. In that case, your error is going to go down by h to the power p plus 1. Error in the displacement is going to be of the order of p plus 1. And what does that mean? Right here, when polynomial order was 1, the error was p plus 1, which is equal to 2. If you're using quadratic elements, your error will go down by 3 orders of magnitude when you increase the number of elements. But the error in the derivative is of the same order in general of this polynomial order. So this is something that I'm just stating without trying to prove or do anything. But this is for your knowledge. When you try to implement something, you should know: can I just keep on increasing the number of elements or the polynomial order? What happens? Okay. All right. So there is this a new topic, variational methods. So till now, what we've been doing has been derived from a method of weighted residuals, right? So we said that we'll take our differential equation, multiply it with u bar, integrate it by parts, and so on, and we'll get our matrix equation k d is equal to f. So all that was method of weighted residuals. But all that can also be sometimes derived from what are called variational methods or energy principles. So again, whenever you hear the word variational, you should think of energy principles. And the specific sections in your book by Reddy, this book tends to mention this variational methods again and again, but essentially uses only method of weighted residuals. So these are the sections from the Reddy book and from the Jumsted's book, chapter 9, which I'm guessing most of you did not get to last time. So there is some more information about this. We are not going to dwell too much into it, but you should know when people say what are variational methods, you should know what they're talking about. So one simple example to understand these energy methods is this. Let's say we have a spring hanging from the ceiling and we have a mass we are attaching to the spring, and we want to find out what is the displacement. So the method we would normally do is write the equilibrium equation, which is the same as method of weighted residuals or the principle of virtual work. So what we do is draw a free body diagram, and in the deformed configuration, the force acting on this mass will be mg downwards. The spring force would be k times d upwards, and you can find your displacement like that. Now, in terms of, this was the way that we normally do using equilibrium equations. But the same thing you can end up with by using a alternative principle of the minimization of potential energy. And how does that work? We say that the total potential energy of this system, the total potential energy of this system is going to be the sum of internal strain energy and external potential due to external forces. So this is something that internal energy stored within a spring after it displaces by amount d is given by half times k times delta square. And this is the potential energy for an object. If you have an object at a height h, if you raise it, we increase its potential energy, right? So in this case, if you decrease the height by d, that's why we have minus mg times d. This is the amount by which it will decrease. That's why we have a minus sign here. So this is the total potential energy of this system. And if we minimize it, we are going to try to minimize it with respect to d. We are saying that what is the value of d at which this potential energy is minimum? So that equation is simply take the derivative of this potential energy with our solution vector, the solution d, and put it to 0. You get the exact same equation as the equilibrium equation. Okay. So there is an equivalence between these two, but there is a caveat also. If there is a potential energy function, you take its derivative, you will get an equilibrium equation. On the other hand, if you have an equilibrium equation, it is not always possible to construct a potential energy functional corresponding to that. Okay, there are problems in fluid mechanics or friction or there are lots of those kinds of systems where the concept of potential energy cannot be implemented. But in structures, most of the times we can talk about existence of a potential energy function. So another way to take a look at this is here. So I'm plotting this potential energy, total potential energy with respect to displacement. So if I pull this thing down, the energy within the spring, this u, this is the black line, this will increase. On the other hand, this potential energy due to the external forces, this is a straight line with a slope of minus mg. Okay. Now, the equilibrium configuration is where you take this curve u and you add this curve, the straight line due to w, you will get this blue curve. And this blue curve goes minimum at this point. So this is the solution. Okay, so let me try to ask you this. So keep a note of where this displacement is. And if this spring is, let's say if this spring is more stiff, then the potential energy function in the spring is going to increase faster. Does that make sense? If the spring is stiffer, then the potential energy of that spring is going to increase faster. And what that means is that the d, the equilibrium point, will be smaller than the one before. Does that make sense? So originally our displacement was here, the equilibrium point, that d was here, but if the spring is stiffer, then it displaces less. The same thing happens if the spring is softer. So if the spring is softer, the internal energy, strain energy raises slower, and we get more displacement. Okay, so this is just a way to visualize the same thing. But now let's try to apply the same concept to our one-dimensional problem. Okay, so the one-dimensional problem that we had was div s plus b is equal to 0, where I'm saying that if c is constant, then what we will have is c u double prime plus b would be 0. So this is the problem that we are trying to solve. And if we try to write out the potential energy for this system, we can again write it out as the strain energy, internal strain energy, plus external potential energy due to body forces. And it is important here to note that these body forces have to be conservative. So what does conservative mean? It means that it is path independent, meaning that if I have some object at this place, and if I take it to a new place like this, versus if I take it to a new place like this, if I go through different points and end up at the same final place, then the potential at that point, potential difference between those 2 points is independent of the path. That is your conservative body forces. Okay. And then how do we find the strain energy stored at any point in the at any point x in the domain? What we'll do is we'll find out the strain at this location. The strain at this location is going to be u, the derivative of u. U is the displacement, derivative of u is strain. Multiply that with c, you will get stress. So the strain at any point is going to be denoted by half times stress times strain. At each and every point along the bar, this is the strain energy stored at that location. And if you integrate it over the length, this is the total strain energy stored in the bar. Okay. So this quantity integrand right here, this is also sometimes called the strain energy density. And if you take that strain energy density and you integrate it over the domain of the bar, then you get the total strain energy stored in the system. And that can be simply expressed as half times strain squared times the Young's modulus. And similarly, we have the external potential due to body forces, and the same minus sign times displacement at x times body force at x. You integrate that along the length, you will get the total potential due to external body forces. If you add that up, you will get this thing. This is the potential due to, this is the total potential energy of the system. Okay. And just to let you know, there is, in the Reddy's book, they use the notation IU, which is essentially the same thing as this. And in Jumsted's book, he uses the notation script E, which is a functional of U, which is also the same thing. So if you're reading that book, you don't need to be, you can relate those quantities with this. All right, so finally what we have to do is to minimize this potential energy. And let me just briefly go over this. So to minimize the potential energy, we have to minimize it with respect to u, not with respect to x. Okay. So in order to minimize this potential energy with respect to u, what we have to introduce is something called a directional derivative. How many of you have seen this directional derivative before? In mechanics? Okay. So this directional derivative, which is also called sometimes a Getio derivative, what this helps you to do is to minimize a functional with respect to a certain function. So let's say you have a functional j, that this is how this directional derivative is defined. So this functional j, or in our case, this is a functional pi of a function u. If you want to minimize it with respect to another function, you can simply write this out like this. So the input of this functional u is just added with some small number epsilon times u bar. This is the same virtual displacement that we had before. You calculate your new functional with respect to this as the input, take its derivative with respect to epsilon, and finally after you take the derivative, you set epsilon equal to 0. So this is just a definition. And a more physical interpretation of this derivative is, or this directional derivative is like this. So let's say, let's consider a function f of a variable x. So this function is nothing but a sphere. This is a definition of a sphere. Okay. And if you take the gradient of this function, you will get twice x, and x is radial. So what that means is, if you have a function f, the direction of greatest increase is radial direction, right? So all these circles, these are values of constant f. So what that means is the gradient is going to be perpendicular to the direction of the constant f. And if you take that gradient and dot it with some another vector y, if you take that gradient and dot it with another vector y, that will tell you how much does f change in that direction. So that's why it is called a directional derivative. Okay. All right. So let's stop here, and we'll continue on Friday.